Hello everyone, hope you had nice holidays. We have a first contest of we are to 2026, contest 11. Not that many people participated this time. Okay, maybe they're still on vacation, but again, we have some team. Okay, Wild Dumplings, nice name. I've usually disabled team participation, but I forgot probably. Okay, so I tried to do it to make this contest not very hard, and okay, so by the judging by results, it yeah, it's kind of okay. But some people did solve only few problems. I believe these problems are also quite kind of easy. Okay, we'll see. We will see what happened. Also, I said time. I set the time of the contest as to 5 hours. So some people solved it more than 3 hours. It's not what expected. So it was supposed to be 3 hour contest. Okay, but okay. Hope you you don't regret spending that much time on this contest. So let's go. First problem is pretty simple, but I spent too much time solving it actually because okay, it's simple implementation problem. So you basically you have some airplanes. You know how many empty seats are in every airplane, and you pay the amount of money equal to number of empty seats. Yeah. And the question is, what is the maximal and minimum sum you can spend? And it's obviously can be solved using some greedy approach. Yes, so if you want to either maximize or minimize, you can just pick the minimal one or pick the maximal one. It's okay. So I won't prove it. It's just obviously correct in this case. But okay, so the constraints are small, so I decided to do it in this very simple way, just iterating over every. You don't need any data structures to find the minimums. You can do it just one by one because so you need to pick 1,000 seats, and every time you can iterate for all 1,000 planes. So it will just in million operations you will do it. So I decided I will do it in very stupid way, and again I spent too much time doing it. Let me just keep something moving. Something like this. So I wrote a strange code which so here I pick the maximum. Then remove it, and here so because you can't pick empty plane, so you need kind of like something like this, and I implemented incorrectly, and I spent too much time finding these mistakes. Okay, probably there is some much easier solution for this problem, which I missed. Okay, so it's me just trying to understand what's going on. So in the end, I do something like this. So I just iterate all planes, I skip the empty planes, and if plane is not empty, then I check if it is less than my minimum or something like this. Just use set heap. Yes, probably using heap or set would be better here. Even if you don't need them for the time complexity, it probably would be better just for the clarity of the code. Yeah, because you have data structure which can give you minimums or maximums. But again, that's my solution basically. Let me show you my solution actually. Problems. So no, it's not that not that long as it may be. So so I basically have two parts. In every part, I pick the minimal or maximal plane, which is not empty, and just take one seat on this plane. Here I took maximum. Here I took minimum. That's it basically. Not that difficult. Let's probably look at your solutions. Does anyone have very simple solution? Okay, 3 minutes. Oh, I need to enable master. Yep. Oh, okay. We have priority queues. Oh yeah, realize using priority queues actually make code kind of easier. Yes. So every time you just push it and it give you the and but you need two priority queues, one for minimum, one for maximum. Yeah. Okay. Makes sense. Makes sense. Okay, it's just the first problem, so I spent maybe more time than I need to. So I spent like 5 minutes on this problem. Not a great result, but again, it's just first problem. Sometimes sometimes you spend too much time on the first problem. It's okay. Second problem. It's about keys. Yeah. Second problem again is kind of implementational, but implementation is kind of easy. But what you need to do, you need to find how many keys you need to buy before you start your journey. And the idea of solution is that you don't need to buy them in the beginning. You can buy them on the go. So you just simulate what you need to do. Every time you need some extra key which you don't have, you just say, okay, I need the key now. Let me buy this key in the beginning of the process. Yeah, and like this. So it's kind of I believe the trick here is that you don't need to buy keys in the beginning. So instead of buying all the keys in the beginning, you can buy them during the process, and the result will be the same. Yeah, and after you learn that you can buy keys in the process, you just simulate all the thing, and that's it. So I do it like this. I make the counter of how many keys for each letter I have. I have 26 letters. For every letter, I remember how many keys of this type I have. I go here. So every time I use the key, or I take the key, and then I use the key. If, okay, stop. Oh, show me. So every time, if I don't have the key, then I need to buy it. So I buy this key, increase the result by 1. And then I use this key. That's it. So that problem was much easier for me for some reason. So it's not that implementational heavy. So that's the whole code actually for the second problem. Okay, let's get. I don't think you have something more simple than this. So that's it. I hope it's clear enough, right? Do you have any questions? If you have any questions, write them in the chat or something. Okay. Okay, let's go to the next problem. We have some interesting problems later, so let's go to them. Problem C. Problem C. Okay, problem C is a nice problem. So you have a string and you have some number of changes of the letters, and every change like swaps 2 letters. So I take all occurrences of some letter and change to some another letter. And the trick is, okay, so you can, I believe you just, if you just do it one by one, yes, it will be time limit. Yeah. So if you just, for every swap, you iterate over whole your string and make these swaps, it will be too slow. The idea is to keep track of every equal letter. So if you look at all equal letter in the beginning, they all stay equal. Yeah. So you just group all the letters by the same type and process them as a whole. So you take all this set of all same letters, and for all these letters, see what will happen to them in the end. I do it like this. Okay. I misread the problem statement, so I will do stupid mistakes, but doesn't matter. So I have this array P. So you can make it of size 26. Actually, you have only letters. I decided for simplicity I will do it on size 20. So I do arrays for all possible characters. Okay, this array is too large. You don't need it actually, but it's okay. How we do it if instead of updating entire string with particular range? Oh, it would be much more fun problem. Then I believe if you do it for particular range, you need to do some segment trees on top of that thing. That would be much more fun. But here we don't do it. We do only global change. So we change all letters of the same type. So here I actually don't know how to read single characters, so I read it like this. So I read them as strings of one character and then just take characters. It does look very nice, but I don't know easier way to do it. Okay. Yeah, so I have these 2 characters. Okay. Now I iterate over all letters and see if this letter is now pointed to A. So if PC says for initial letter C, what is the final letter? So if this final letter is A, swap, yes, I misread the problem statement. Yes, I told you. I thought it's not swap. I thought you just put X to Y, so that's why. Yeah. I thought it's one directional. I thought you swap all letters X with letters Y, but you actually swap them. You make X equals to Y and Y is equals to X. Yeah, my bad. Yeah, you can just find the indices and swap them. Would be much easier, much easier. Yeah. But again, it doesn't matter. So it can be done faster here. Yeah. So instead of this, I have only one position for each character. But every time I have permutation, actually. Yeah. So you need that, like, swap two elements of the permutation. And yeah. Because I didn't know I have permutation. I thought I have only one, only this substitution. Yeah. So I don't have permutation. So I need to kind of find all of them. It can be done easier actually than this, but I decided it's okay. So again, you can speed up this solution by like 26 times, yes, but you don't need to. So like 200,000 multiplied by 26, it's small enough. You don't need to speed up. Sometimes, again, speeding up solution is just will make your solution less clear. Yeah, yeah. That's it. So that's basically the whole code. So I maintain this permutation every time I make a once, but here I make a swap actually. It's just slow method of making swap of two elements in permutation. And that's it. In the end, I just construct. So for every initial character, I find what will be the final character, output all these characters, have the final result. Yeah. Again, the idea of the problem, the only idea is to keep track of all characters of the same type. Yeah. You don't need to keep track of every character, but for all characters of the same type. That's it. And you have only 26 types, so it's easy. Yeah. That's it. That's problem C. Let's go problem D. Where's problem D? Okay. Code Force actually became much faster lately. So I don't know what they did. So they probably optimized something, but now it's actually open faster than before. But still, tree. Okay, I didn't draw the picture. Let me draw the picture here. So what we have in this problem, we need to build a tree. Where's my? I forgot my pen. Where's my pen? Oh, here's. So you need to select availability early. Okay. So you need to build a tree. You know the diameter of the tree. Oh. So you know the diameter, and you know the height of the tree if you hang it on the if you root it in vertex one. Yeah. So if you vertex one, you will have something, and this height is h. Okay. And the question is to just to build any tree with these parameters. So you have parameters n, number of nodes, d is diameter, and height of the tree rooted in vertex one. And you need to build such tree. And my idea was very simple actually. So no, let's do it like this. So yeah, let's take vertex one. Have a sequence of nodes. So we need to have this sequence, yeah, of length h. Yeah. Now, if diameter is more than h, then let's add another part here of size d minus h. Yeah. Now the height is h and the diameter is d minus h. Yeah. And you can do it if this d minus h is less or equal than h. Yeah. It kind of makes sense. It says this diameter is not greater than 2h. Yeah. It makes sense. You can't make diameter more than 2h if you have height equal to h. Yeah. Now, the only problem here is that I have parameter n. So I have some extra vertices, yeah? And you need to hang them somewhere. And I decided I will hang them here. So all other nodes will be here. Yep. Yeah. And when I started the programming, I actually thought that, okay, this all works if this height is at least 2. If height is 1, then I need to take them here and then diameter equals to 2, yes? So if diameter equals 1 and n equals 2, it's kind of special case, yeah? So you can make this. If n is greater than 2 and the diameter is 1, you just can't build this graph because the diameter will be at least 2. Yeah. So that's kind of special case. It's not that hard to track. That's it. So let's just program this. Again, first, usually I want to try to check all the corner cases here. So corner cases or d less than h actually doesn't matter because d is greater than h here. Yeah. So you don't need this. If d is greater than 2h, it's impossible. Yeah. Also, there's another special case which I will edit later. Yeah. Now I will just so that's basically the picture. I will do it like this. I will do it like this. I will make vertex 1, then add vertices like 2, 3, 4 here. And then add next vertices here. So like 6, 7 here. Yeah. And then all the rest I will add here. That's the plan. Yeah. So you have three groups. This one group, this another group, and this the last group. Yeah. Okay, here I think too much about what is the best way to do it. Here I'm trying some. I just trying to guess what number I need to put here, but I then decide okay, it's much easier to just pick nodes one by one because again I forgot how to keep track of which numbers I use, which numbers I don't use. So I will just have variable of the first value just not used. Yeah. So every time I just increase it and take the next number, next unused number. Yeah. So I hang all these numbers in a chain here, hang the next number to the one, and hang all the other numbers in a chain here in this chain. Yeah. And now all the rest numbers I will hang to these numbers. So this number is h, right? Yeah. No? Yes. Okay. Yes. Yeah. That's it. So this number is 1, this number is h, this number is h plus 1 actually. Okay, doesn't matter. This number is h plus 2. Yeah, something like this. Very simple code in the end actually. So that's it. So that's the whole code. So you make one chain, another chain, and then just hang everything else to some special node, which doesn't. So it's important to hang here because it doesn't increase the diameter. Yeah. So you wanna find place which is not the end of the diameters. Yeah. Yeah. So basically, you can pick any node which is not the end of the diameter. This is why d equals 1 is special test. Yes, because if d equals 1, then both nodes are end of diameters. If you add any node, you will increase the diameter. Yeah? If diameter is not 1, then you have some middle node. You can link everything to this middle node. Yeah. Okay. Oh, problem E. Problem E is actually pretty standard dynamic programming problem. I actually made mistake in it, but yeah, it happens even with me. Yes, I solved like 1,000 problems like this, but still I make mistakes, stupid mistakes. So what we need to do? We need to find the string with maximal cost. Yeah, and we can make at most k substitutions. Yeah, so we can replace. Yes, we can change at most k letters. And we need to maximize total cost. Cost is calculated like this. So for some pairs of consecutive letters, we have some assigned bonus, yeah? And we just sum all these bonuses and have the total cost. So again, the problems like this, you have the string, you go left to right. Okay, I guess that's all the solution. So you need to change some letters. So let's go left to right and change some letters. What we need to do, so if we already did something with this prefix, we need to remember how many letters we change, yeah, and what is the last letter here, yeah. So you have dynamic programming of two parameters like ij. How many letters I already change, and what is the last letter here. And then you add one another letter. You can either keep it or change it, yeah. And you just calculate what will be the total cost if I go here and then use this letter. So you add this bonus to your cost and update dynamic programming. Pretty standard thing actually. You don't need to optimize anything actually here. So my solution will work in time complexity. So my solution will have like this. So I do it for all the characters. I have 100 characters. For every characters, I update this matrix of size 100 multiplied by 26. Yeah. And for every time, I will pick all possible next letter by another 26. Yeah. So I will do it like this. So for every character, every number of changed letters, for every character in this position, every character in this position, I will calculate them programming. So that's my time complexity. And it's okay. It's small enough to fit into time limit. I believe you can eliminate this part actually. Yeah, I believe you can do it. So if you pick this last letter, you can actually find the optimal previous letter faster than it can be solved fast, I believe, but you don't need to. Okay, got it. So n is not the line, n not the size of the string, n is number of these pairs. Yes, okay, I got it. It's strange naming. Usually n is the size of the string, but here n is number of these pairs. Yeah, and you actually don't need this number of the pairs because I immediately transform these pairs to some two-dimensional array for simplicity. Okay, so that's how I normally write dynamic programming now. I used to do it differently, but now I usually do it like this. So again, I have this two-dimensional array, and I will replace it. So every time I pick new character, and I replace this two-dimensional array. Yeah. So this two-dimensional array is my current state. Yeah, for this position. Then I add one more character to my string, and I go to the next state. So I will replace this two-dimensional array with another two-dimensional array. I also spend too much time thinking what to do with the first character because first character is kind of different. It doesn't have previous character, so you need to somehow do it differently. In the end I decided so I will add some special character at like beginning of the string, and I will start with this special character for simplicity. So you don't have special ifs here. Yeah. So basically, again, I added one more character to my alphabet and put it in the beginning of the string. So I always have the previous character. Okay, so what we do here? So I iterate on my two-dimensional array for all my states. So I is number of changes, j is the last character. So int min is just impossible state. If state is impossible, just continue. If it is possible, then I believe in this problem we don't have impossible states actually. No, if 0, okay. For k equals 0, I can have impossible states, but it doesn't matter. So if state is possible, I see what I need to do. I can either keep this character or replace it. Yeah. If I keep it, then this. Then I go to state ix, and the new cost will be idij plus the bonus. Yeah. And I just update the maximal possible cost. Yeah? That's it. If I replace it, so now I can replace it only if number of operations less than k. Then I can make one more replacement. I make this replacement like this, and again, that's basically, yeah, it's all the same. So I make I make I plus 1 replacements, and the final character is y. So I update this state, and the cost will be this cost plus cost of the pair j and y. Yeah. strange naming, actually. I use strange names for variables here. But, yeah. It's because that's because I'm in a hurry usually. Basically, that's the whole solution. Again, pretty standard dynamic programming. Pretty standard. After you solve, okay, we need to have special contests about dynamic programming, but a lot of dynamic programming problems looks like this. Now I have wrong answer test for 44. Can you find the bug in my solution? Very stupid bug actually. Can you find the mistake? Normally I would think it's integer overflow, but this season I moved to 64-bit integers. So now I don't have integer overflows that often, as often as it was last year. So it's not integer overflow, it's just stupid mistake. Can you see the stupid mistake? I kind of thought that mistake should be, yes, here it is. Yeah, there are negative numbers. I didn't see it when I read the problem. It kind of doesn't make sense to have negative costs. Why you have negative costs? But again, another case, why not? Why not? Yes, so this cost may be negative. Yeah, so you can't initialize minimum as 0. Yeah, you need to initialize it with something negative. Yeah, so you need to replace the 0 with minus infinity. Good. So then I spend a lot of time thinking what's going on, reading this solution over and over again, and then finally, no. Okay, spend too much time. Yeah, finally I find the mistake, but again, spend too much time finding these mistakes. Okay, that's it. That's what problem E. Good. I probably should have saved this problem for dynamic programming contest, but okay. Problem F was very, very good. Okay, I don't think it's for me. It's a kind of standard problem. Do you think it's really good? Okay, maybe because I solved too many problems like this. In problem F, what they told you is actually that you need to so they describe something strange here. What they told you that you need to put bosses in positions that you can't avoid. Yeah, so you have a graph. You move from one node to another node. So you choose some node S, you choose some node T, and you move from here to here. And if there is an edge which you can't avoid, so you always need to you need to visit this edge, then you put a boss here. Yeah, and you need to find maximal number of bosses you need to put. Solve something like for first time. Oh, good for you. So that's good. So if you solve, and did you solve during the contest? It's good. It's good. Yeah. So, okay, if you know something about graph theory, so the edge which you can't avoid is called bridge. So the question is not bridge for the first time, but dp on the face. Okay. So this edge called bridge. So what you need to do, you need to find two nodes. So number of bridges between them is maximal possible. Yeah. So you need to find node S and node T. So if you look at the path between them, so there are a lot of bridges here. Yeah. Again, you have some components here, some components here, some components here, but these edges are bridges. You want to maximize number of bridges. Again, if you think about this problem, so what you know about bridges? Bridges actually split your graph into by connected component. Yeah. So you have some B connected component. Let's make something. So you have component 1, Then you have bridge. Here you have another component. Yep. Up, up, up. Then you have another bridge. Here you have another component. Okay, let's have some triangle here for simplicity. Another up, 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 and some bridge here, and some another component here, and some bridge here. Pop up component. And this is component of the single node for fun. Yeah. So so bridges split your graph into by connect component. Yeah. What you can do, you can actually build this decomposition. So you can find all the connect components and build what's called a big connectivity decomposition. Yeah. So you can for each component you can replace it with the node and build this decomposition. Yeah. So every graph in terms of big connectivity can be represented like this. You find all the edges, or you find all the bridges. Yeah. Now these bridges split your graph into bconnect components, and if you look at how these bconnect components are connected with bridges, so this structure of bconnect components is a tree. Yeah. Okay. So if you didn't know it before the contest, that's how it works. Yeah. So every graph in terms of bconnectivity is kind of a tree. Yeah. So you have components which are bconnected, and they connected with bridges, and this structure of bridges, it is a tree. Yeah. Now, what we need to do, we need to find two nodes, pick nodes S and T. Yeah. So if you look at the connect components of this node S and node T, then number of bridges is just distance in this tree. Yeah. So here I have 3 bridges. Again, if I pick node S, anything from here, if I pick anything from this component and anything from this component, yeah, then again, any path will contain three bridges, 1, 2, and 3. Yeah. So what we need to do, we need to find a diameter of this tree, basically. Yeah. So what you can do, how you can solve this problem? You can find all the bridges, split graph into bconnect components, build this tree, and then find diameter of this tree. Okay, so every part is kind of standard. So if you didn't see one of these parts, you need to invent it during the contest. Okay, but if you how to find the diameter? Many ways to do it. Yeah, you can do it using dynamic programming, or you can use cheating using just DFS, like I usually do. How I usually find the diameter? You pick node 1, then find the farthest node from node 1. So maximal distance. Yeah. And then take node X, find the farthest node from node X. And this is your diameter. So you find the farthest node from node 1 and then farthest node from node X. And this is your diameter. And because for every node, if you look at the farthest node from it's always one of the ends of the diameter. So you find one end of the diameter and then find another end of the diameter. That's how I usually do it. I think it's just easier than do dynamic programming. You can do it using dynamic programming also, no problem. Okay, so these are all the bricks which you use to build the solution. Yes, you need to find the bridges. You need to find the diameter of this tree. That's it. Yeah. So let me split it. I didn't build this tree explicitly. So instead of building the tree, I do this second part on the whole graph because I can. You'll see. So here I just standard code. So this is standard code for finding bridges. Yeah. So I remember the entry time. I remember the link to the farthest node above, which reachable from my subtree. Yeah. Skip the parent. If it's not visited, then I visit it. Take the maximum minimum over here. If it's already visited, take minimum of this and entry time of this node. This code is very standard. Okay. Now I will add something which is okay, it's also standard, but that's not that popular probably. I will add operation which finds all the bconnect component. To do this, I use the stack, so I maintain the stack, and every time I find the bridge here, I pop everything from the stack and make another connect component. You can do it, you can just you can find all the bridges, remove them, and then find connect components. They also will work. I just do it like this because it's easier for me to do it like this. Up to you. So here I will just, okay, so here, when I find the bridge here, I take all the nodes from the stack up to node Y. And they will, okay, so let's show me what's going on here. So if you didn't see it before, so in my DFS, I have node X, then I go to node Y, then I see that in this subtree, I have no edge which goes upward. Yeah. So this edge is a bridge. Yeah. So when I find the edge is a bridge, I just take all the nodes here which are not marked yet and put them in as a separate bconnect component. Yeah. To do this, I just put them in a stack here in the beginning. Yeah. So my new so again in my stack, I have this stack. So in my stack, I put node X, then put node Y, and then something else. Yeah, after node Y. So all this something else is my next bconnect component. Okay. I'm out of letters. Yeah, so I reuse the same letters. Okay, that's it. So that's how you do it. Now I colored all the bconnect components. Now the edge is a bridge if it connects the vertices of different components. So you can easily check if some edge is a bridge or not. And then I will just second DFS. So I do it like I will do it for the trees, but okay, I just check. I didn't screw up here. Yeah, so second DFS will do this. So it will find the farthest node from here. Yeah. So I will do it like on a tree, but my graph is not a tree. Yeah, but I don't care because I only care about bridges. And in terms of bridges, it is a tree. Okay, doesn't matter. It's very strange way to do it. It would be probably more clear if you just build a tree and then run DFS over this tree. But I decided I will do it like this because it's faster to implement. So I usually do it like this. So I have DFS over tree, which returns a pair, maximal distance and the node with maximal distance. And I give it a node, a parent, and distance. Here I don't need parent because it's not a tree. Yeah. Yeah. Yes, I don't need parent here. Finally, I don't need parent because it's not a tree. For DFS over trees, I have a parent in this recursion, right? But here you don't need it because you have this array of marks here. So that's the whole. Yeah. So that's the whole DFS. Yeah. So it will run DFS over the whole over the whole graph and find the node with maximal distance. Yeah. Okay. Not very canonical implementation, but it works. And then I just run it twice. So I run it from node 0 and then run it again from node X. Just for consistency, replaced it again. That's it. You see, I run it first from the node 0, then second time from this first node X. Second value is the node, and first value is the distance. Yeah. So you need to output the maximal distance. You need to output size of the diameter. That's basically it. So this first DFS to find the connect components, and second DFS to find the diameter. Good. Let me read your solutions actually here. Oh, someone who has nice solution. Let's review. You have DSU. Okay. Okay, this code I know. So that will find the bridge. Yeah. Okay. So you just make set of all bridges. Also will work. Okay, then you take all the no all the edges, and if it's not a bridge, then you can compress connect components. So that's how you compress be connect components. That's another way to do it. Okay. Mm. It's okay. It's okay. That's the same DFS as mine. Yes. You just have these global values. Okay. Okay. And you run it twice. Yeah, basically the same code. Uh, what? What's this? Here is calculate levels, right? Nothing. Okay. Hmm.
It is basically that if there is a backedge, and then in the DFS tree, I add +1 to the entire path that the backedge covers. So if there is a bridge,
Ah,
then it won't be any backedge. So dp of v will be 0 and its
uh-huh.
parent in the DFS tree. So that will be the bridge.
Got it. Got it. Okay, yeah, it's a little bit harder than mine, but yeah, it will work. Good. Good. Okay, we have last problem left. Okay, so to have two problems here, but it's actually the same problem. Uh, uh, just easy and hard version of this problem. Okay, easy version is really easy. So this classical problem of bulls and cows. Okay, so you need to guess a four-digit number by making guesses. And every guess, they tell you how many digits stands on it. It's basically like Wordle, but slightly different. Um, so what I want to say, I want to show you how I usually implement interactive problems, because in the interactive problem here I decide I will show you how I normally do it, because one of the problems for interactive problems is how to test them, how to debug them. Yeah, so I usually start by making a simple interactor. So instead of having this interactive protocol, when I output something, read something, I write something like this. So I write this procedure ask that will simulate the interactor. Yeah. So I will not do what's written here. I will just calculate what interactor should tell me if I ask this. So I hide this secret. Yeah, here. Yeah. And I just calculate what interactor should tell me if I get this request. Yeah. So I don't make real requests. I just simulate interactor, and it actually will make the life much easier. So it will allow you to test your solution many inputs and see what it actually works without spending too much time of interacting, like playing with your program. Yeah. uh, can I spend too much time figuring out what is the easiest way count a number of this the second number. Okay. I decided to do it like this with sets. I will replace it with vectors because I will get time limit in future. Yeah, so I will replace it with vectors. But okay. As a first version, it's okay. Okay, so here I make sure I don't over. So when I guess correctly, so I get answer 40, you need to immediately stop. So I just decide I will just make it here. So every time if I receive answer 40, I will just immediately stop my program. Yeah. So you don't have problem that your interactor stopped and you continue doing something. Just stop your program. Okay. So the first version of this problem is very easy. You have 50 requests, so you can do it like this. For example, you can check all the 10 numbers of 4 equal digits, and if the answer is okay, answer will be okay. It will be 10 actually. Okay. So interactor will basically tell you if you have this digit or not. Yeah. So if you have this digit, then you and now you have 4 digits that are in your number. You just need to find in which order they are in your number. And I decided to do it like this. Okay, we have 24 permutations. I spent 10 requests here, so I have like 34 requests in total. Good enough, less than 15. So why overcomplicate things if you can not overcomplicate things? And now I just test it. Okay. I spent too much time thinking what's going on. Something really strange is going on. Yeah. Now it's much better. No, you see. So again, so I make first 10 requests, finding which digit I have, and then I get another like at most 24 requests to try all the permutations. Okay, now when I tested it, see that it works. Yeah. Now I will just replace this one function. Yeah. So instead of this function, I will make function that really asks the interactor. Yeah. So I comment this, make another. Yeah. And here I actually implement what need to be implemented for the interaction. So I output these numbers. Don't forget. So handle will flush the output. It's important. Okay, read this. Okay. No, I just tested. Okay, spend some time testing. That's it. So okay. Okay. It will pass. Okay. So that's the easy version. So easy version, you just check all the digits and then check all the permutations. For example, yeah. For the hard version, you have only 7 queries. So I was thinking about some interesting solution, but then I decided I would just do it greasily. So greasily, what I mean greasily? So what's happening here? So you make some requests. Yeah, that request will so you ask something. You say like 1, 2, 3, 4. Yeah, this request will give you different results. So it will give you a graph like, for example, 0, 0, or like 0, 1, or like 1, 0, or and so on. Yeah, depending on which result you have some subset of possible answers. So you have like a lot of answers, possible answers. You have all 1, 2, 3, 4, 1, 2, 4, 3, and so on. So you have all different combinations here. Then you ask something. Then you kind of, depending on the answer, you split all your possible answers into some groups. Yeah. And what I will do, I will try to find the question which splits in the best possible way. Yeah. So I will split, minimizing the maximal size of the group. That usually works. Yeah. So again, I want to minimize the worst case. Yeah. So I want to have my set of the smallest possible size. So I will just always pick the question which will make my size of my set smallest possible in the worst case. And I just hope that 7 queries will be enough. That's my plan. Okay, so I don't know why it's 7. I decided that it should work. If again, okay, here is kind of into here I actually count how many have okay. I have 5,000. I thought, okay, it's a square 7 queries. Every time you have several postcodes, so it should be enough. Okay, I would call it educated guess. Let's say that's how people who try to look smart, they call it something like this. I call it just intuition. Yes, so I think that 7 should be enough. If not, I will adjust. Okay. Sometimes it depends on the problem. In some problems, judges actually make very strict limit. So they like ask you to make 22 requests, and they can prove that 22 is the minimal possible number of requests. So it's impossible to do 21 requests. Yeah. So you need to be very careful. Here I decided it's a classical problem. What can go wrong? So here I make list of all possible combinations, and then every time I will pick one element and try to make this query and find the best possible query. Okay, here I make function that calculates the result. Here I make here I forgot to change this S to B. Okay. Okay, here I decided, okay, it looks scary, so I will replace my normal 64 bits integer with 32 bit. So because I have vectors of 4 integers over and over again, I should have simplified it already here, but I decided, okay, it's okay. I will get time limit in the end. I will show you. Normally, I usually implement somehow until I get time limit. So if I get time limit, then I optimize. But here I already feel that it should get time limit. So I try to optimize on the go because of the feelings, yes. Because sometimes you have intuition that it's already too slow. So you need to optimize it to fit into time limit. Because you have 5,000 elements. So you kind of need to check all combinations. So it's like 25 million pairs. For each pair, you need to count this function. Yeah. It's already not very fast. Okay, this stupid code is not very fun. Let's skip it. Okay, let's find for so here. So what I'm doing here, okay, I will move it out of the. I don't need recursion because I thought I will have some recursive function, but then I decided why I need recursion if I have only one option. So I make query and then move only to this subtree. Yeah. So you don't need all this decision tree. You move only to one branch of this decision tree. That's my job. So what I'm doing here, I check all the possible answers. I decide it would be nice to ask queries which are possible answers. It kind of makes sense, yeah. So I try to find the best possible question to ask, yeah. So I try all possible questions, look at all possible answers, yes, group them by the same result, and find the maximal group. And then find the question which minimize the size of the maximal group. That's what's happening here, okay? And then just continue. Yeah. Just so I ask this optimal question, find all the answers which satisfy which give the same answer, and move to this group. Okay. That's it. That's basically the whole code. Then I run it, see it, it kind of slow. Okay. I look which part is slow, and just the first part is slow. Then I try to speed up it because I already see it's slow. So what I speed up here, okay, I look at what's happening. So okay, what? Yeah, so I make this first strange break. So in the first step, it doesn't matter which question asked. So all first questions are kind of the same. So in the first, as a first question, I just ask the first question, any possible question. We assume that each of possibilities is correct. What do you mean correct?
Compare every possible string with every possible other string.
Yes. Yes, I compare all pairs and pick the question which spreads all the answers into small groups. Something like this. Yeah. So for each possible question, I find for which answer I get the maximal possible group and minimize this maximal group. Yes. Something like this. Okay. Again, slow, Okay. Then I decide, okay, I tested my program with O0. Maybe I need to test it with O3. Run again. Okay, now it's faster. Yeah, see. Then I looked here and see I have S instead of B. Oh, that was embarrassing, actually. I wanted to speed up this process, and then I found this. Okay, now it's worked pretty fast, you see. So your time limit is 2 seconds. I decided it looks like less than 2 seconds. So I will just submit this. Again, you remove local testing, add this interaction, submit, and then wait, then you wait, then you wait, then you wait, until you have time limit test 99. Okay. It was kind of expected at this point. So I already saw that I have these sets for no reason here. So I'll optimize just removing these sets. So I just right in the middle of the program. So this is so I call this function 25 million times. Yeah. So you kind of need to optimize it. And here I have sets for no reason, actually. So instead of sets, I will use Boolean arrays here. It kind of makes sense, right? So it's the same code, just with Boolean arrays instead of sets. And it will pass. Okay, so now you wait. Okay, it was fun moment was here. So you wait, and then it reach test 99 and waits. Okay. These few seconds were scary. Okay. Okay, and then you wait. Tuk. How many tests? I don't remember. Oh, like 400 tests. And you see it works in a second. So like I speed it up like twice, and now it works fast enough. So that's it. That's the last problem. Let's look at your solutions maybe. Okay, don't look at cheaters. We don't look at cheaters. Who solved it? Okay, that's probably not cheating. Okay, that's unexpected. Why you have this? Okay. 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 It only works if you have if all numbers are distinct, right? It's actually fun. I believe it's faster than mine actually. You don't have any additional arrays, just two loops of size 4. Yeah. Yeah. Also very sparkling. Yeah, maybe we need to have a special lecture about interactives. I'm thinking about having special series about some common tricks that you need to know in competitive programming. But I'm too lazy and I don't have time lately, unfortunately. What's happening here? I can read. So Cartesian product. Oh, you can do it like oh. I don't know this feature. Nice. So it's just instead of making these 4 loops, you can do it like this. It's my solution. I do it like this because I'm old school. Like, oh, not this, not this. Where's my? I just normally do it like this. I just make 4 loops. Uh, okay, but you can make a Cartesian product, right? Like I love it. Just set it, but is it also cheating code? No, I don't know. Okay, let's read it anyways. Uh, not that. Okay. That's okay. So okay, that's okay. You already no, okay. You already optimized it on the go, so that's something I would not do. I use normal maps for sim. Okay, so instead of maps, you use arrays here because you want to speed it up. Okay, just my max on it. Okay, basically the same code, but just more fast than mine. Nice, nice. Oh, good for you. Good for you. It's you. Um. You don't have special functions. You just do it like this. Okay, it's hard to test it like if you do it like this. But okay, good for you. Good for you. Okay, thank you again for watching. See you next week.